Hello, I'm Professor von Schmohawk, and welcome to YU. When we first introduced the concept of exponents, we started by defining integer exponents of 2 or greater as the number of copies of the base which are multiplied together. We then used the rules we derived for combining exponents to figure out what the meaning of an exponent of 1 or 0 would be, as well as the meaning of negative integer exponents. It is natural to wonder if there would be meaning to an exponent that was not an integer. For instance, what would be the meaning of an exponent of 1/2? We can use the rules of exponents to figure this out. If we square a to the 1/2, we multiply the exponents 1/2 and 2. This gives us a to the first power, which is the same as a. So a to the 1/2 is the number that, when squared, is equal to a. This is the definition of a square root. Therefore, a to the 1/2 must be the square root of a. The idea of square roots has been around for a long time. Both the ancient Babylonians and the ancient Egyptians knew about square roots. If you want to construct a square object with a particular area, you need to know what length to make the sides. If we call the length of a side x and the area of the square a, we know that the length x, when multiplied by itself, is equal to a. So the problem is to find what value of x, when squared, gives us a. Let's say, for example, that we wanted an area of 4 square meters. Then, by trial and error, we could figure out that the side of the square must be 2 meters. We say that 2 is the square root of 4, since when we square the number 2, we get 4. But 2 is not the only square root of 4. Negative 2 is a square root of 4 as well, since squaring negative 2 also gives us 4. So 4 has 2 square roots, 2 and negative 2. However, a length can't be a negative number. Therefore, we call the positive root the principal square root. We indicate the principal square root of 4 by writing 4 under a radical sign. If we want to indicate the negative square root, we place a negative sign in front of the radical, indicating the negative of the principal square root. And if we wish to indicate both square roots, we place a plus-minus sign in front of the radical. Any positive number has 2 square roots, the principal square root, which is always positive, and the negative of the principal square root. For example, 9 has square roots 3 and negative 3. Numbers like 9 and 4, whose square roots are integers, are called perfect squares. However, the square roots of most numbers don't come out even. In fact, most square roots have an infinite number of non-repeating digits after the decimal point. These kinds of numbers cannot be represented by any rational number. In fact, square roots forced the Pythagoreans in ancient Greece to invent a new kind of number, which they were apparently not very happy about. We now call these numbers, which are not equal to any rational number, irrational numbers. The rational and irrational numbers taken together are called the real numbers, but more about that later. However, even with real numbers, it is impossible to take the square root of a negative number. This is because squaring positive or negative numbers always results in a positive number. There is no real number which, when squared, is negative. Therefore, negative numbers have no real square roots. We saw that if we square a to the 1/2, we get a. We therefore deduce that a to the 1/2 is the square root of a. Likewise, if we cube a to the 1/3, multiplying the exponents, we also get a to the first power, or a. Therefore, a to the 1/3 must be the cube root of a. Just like square roots, cube roots can be thought of geometrically. If you want to construct a cube with the volume v, you need to know what length to make the sides. We know that the length x cubed is equal to the volume v, so we want to find the value of x that, when cubed, gives us v. In other words, we want to find the cube root of v. For example, if we want a volume of 8 cubic meters, then a side length of 2 meters will work, since 2 cubed is 8. Therefore, we say that 2 is the cube root of 8. Cube roots, like square roots, can sometimes be integers. For example, the cube roots of 1, 8, 27, and 64 are 1, 2, 3, and 4, respectively. However, just like with square roots, the cube roots of most numbers are irrational. However, unlike square roots, positive and negative numbers each have exactly one cube root. For example, positive 8 has the single cube root, positive 2, and negative 8 has the single cube root, negative 2. Positive and negative numbers have only one cube root, because when we cube a negative number, we always get a negative result, and when we cube a positive number, we always get a positive result. As you recall, this is not what happens when we square numbers. Both positive and negative numbers, when squared, produce a positive result. When we square numbers, we never get a negative result. Therefore, the square root of 4 can be either negative 2 or positive 2, since either of these numbers squared produce 4. Whereas the cube root of 8 can only be positive 2, and the cube root of negative 8 can only be negative 2. We saw that because a to the 1/2 squared is a to the 1/2 is the square root of a. And since a to the 1/3 cubed is a to the 1/3 is the cube root of a. Like the exponents 1/2 and 1/3, the same logic applies to any fractional exponent, 1 over n. A with an exponent of 1 over any positive integer, n, is the nth root of a, since this is the number which, when raised to the nth power, is equal to a. To write the nth root of a, we can either write a with an exponent 1 over n, or we can place a under a radical sign, with the number n in the upper left. This number is called the index. When the index is odd, we say that the root is an odd root. And when the index is even, the root is called an even root. Let's say that we have an index of 4. So we have a to the 1/4, or the 4th root of a. If our number a is 16, then the 4th root would be 2. Since 2 to the 4th power, or 4 2's multiplied together, are 16. However, 4 negative 2's multiplied together are also 16. So negative 2 is also a 4th root of 16. Just as with square roots, there are 2 4th roots of 16, one negative and one positive. In fact, every positive number a has 2 even roots, one negative and one positive. And just as with square roots, negative numbers have no even roots. Just as with cube roots, there is only one odd root for any number a, and this root will always have the same sign as a. For example, the 5th root of 32 is 2, and the 5th root of negative 32 is negative 2. On the other hand, 64 has two sixth roots, -2 and 2, and there is no sixth root of -64. So far, we have seen that writing any number a with an exponent 1 over n represents the nth root of that number. In the next lecture, we will see that exponents can not only be unit fractions, they can also be rational numbers written as common fractions m over n.